Okay, here's the problem solving video for the unit on integration. Let's get started with question 1. We're given the differential equation dy dx equals x squared, and for part A we're asked to draw the slope field. So let me draw a coordinate plane, and let's see. So it looks like when x is 0, dy dx is 0. So at all points here, I can just put a horizontal line. And then when x is 1, it looks like my slope is always going to be 1. So I'm going to try to make that look good. And then since x is being raised to an even power, whatever's going to be on this side, it's going to be the exact same on this side. So I'm going to draw the same slope of about 1-ish if I can. Yeah, okay, and then when it gets 2, the slope is going to be 4. So the slope is getting a lot steeper, so it's going to look something like this. And the same thing over here. And then if I go to 3, I'm going to get 9. So it's going to be very steep now, nearly vertical. Okay. And then that's part A. And then for part B, we're asked to draw the solution to the slope field that passes through the point 0, 1. It passes through this point right here. So it looks like you have a graph that's going up, and it's going to the right, and then it's going up. So I'm just gonna sketch that. It's going up, it's going to the right, it's going up. I'm just following the curve here. And then this is my graph. It looks like a variant of x cubed. Maybe it's been raised up by 1, maybe it's been compressed. So this is the solution to question 1. Okay, looking at question 2, seems pretty straightforward. We're asked to evaluate the 4 integrals. So let's get started with part A. First, I'm going to distribute the cotangent, because that seems like a good logical first step. So I'm going to get cotangent theta, tangent theta, minus cotangent theta, cosecant theta, d theta. And then look at the cotangent times the tangent here. A cotangent is just cosine over sine, and then tangent is sine over cosine. So both of these cancel out, and this just turns out to be 1. So also the cotangent and tangent, they're reciprocals of each other, and when you multiply reciprocals, you get 1. So anyways, we have 12 plus 1 minus cotangent theta, cosecant theta, d theta. Add the 12 and the 1. And then to simplify this bottom part here, you're going to need to know that the derivative of cosecant is negative cosecant cotangent. So the integral of negative cosecant cotangent is going to be cosecant. So that means I can solve this integral, and I can take the integral of 13 as 13 times x divided by 1, so 13x, and then minus this part. So the derivative of negative cotangent cosecant is going to be a positive cosecant. So this is going to be 13 plus cosecant theta, and this is actually supposed to be a theta, not an x. So I have 13 theta plus cosecant theta, and since this is an indefinite integral, I'm going to have a plus c. And that's part A. So let me erase and we can do part B now. Okay, so looking at part B now, we have the integral of x3 to the x squared plus 1 dx. So we have a x squared term here, and we have an x term here, and this is going to be like a variant of this derivative, so that's a good sign that we should use u-substitution. So I'm going to set a u equal to x squared plus 1, and I'm going to set du over dx equal to 2x. Bring the dx over there. That's du equals 2x dx. And then notice that how here I don't have a 2x, I only have an x. That means I need this to be x dx. So I need to get rid of this 2. I'm going to bring the 2 over to the other side. So it's going to give me du over 2 is equal to x dx. And then I'm going to make the point clear, I'm going to rearrange this first integral. So it's going to give me 3 to the x squared plus 1 times x dx. And so instead of this x dx, I'm going to replace it with du over 2. So that's, and then for the x squared plus 1, that's equal to u. So this is 3 to the u. And then instead of x dx, I'm putting du over 2. And then the 1/2 can come out to make the integral look pretty. And then so we're integrating e to the u, or sorry, not e to the u, 3 to the u. And then you should remember how to do that. It's going to be 1/2 times 3 to the u over the natural log of the base. So natural log of 3. I'm going to write the plus c. And then this is 3 to the u. I'll just put the two fractions together. And the last step is, remember up here we said u is equal to x squared plus 1. Well, I'm just going to plug in x squared plus 1 for u, like that, over 2ln 3 plus c. And we are done with part B. Now let's move on to the next part. And then now looking at question C, we have a definite integral with bounds of 0 and the square root of pi. So it looks like, again, we're going to have to use a u-substitution here, which is really the only thing we know so far. So I'll say u is equal to x squared. Then du is going to be 2x dx. And then looking at the thing here, we have 3x, not 2x. So to make this as a 3x, I'm going to multiply both sides by 3 over 2, meaning 3 over 2 du equals 3x dx. And then now I can substitute that back into here. So I'm going to get, and since we're doing u-substitution, I'm not going to write the bounds right away. I'm just going to say this is equal to the integral of, so this is going to be 3/2 times the integral of sine of u du. And so now I'm going to do this both ways. So the first way is going to be changing the bounds. And the other way is going to be not changing the bounds, not CB. So for changing the bounds, so remember the bottom is 0, the bottom bound is 0. So if I put, so since u is equal to x squared, if I plug in 0 for x, that's going to give me 0. And then if I plug in the square root of pi for x, I'm going to get pi. So knowing that, I'm going to integrate from 0 to pi, right? These are our new bounds, and the function is going to be sine of u du, and the derivative of sine is negative cosine. So that's going to be, oh, and still have the 3/2 here, don't forget the 3/2. That's going to be equal to negative 3 over 2 cosine of u, and then evaluated from 0 to pi. Plugging in, so negative 3/2. And then cosine of pi is going to be, remember your unit circle from pre-calc, cosine of pi is going to be negative 1. And then we're going to subtract cosine of 0, which is 1. So this is negative 3 over 2 times negative 2. The negatives cancel, 2's cancel, and we're left with 3 as our answer. And then now let's see how we'll do it without changing the bounds. So we still have 3/2 times the integral of sine of u du. But if I integrate this, I'm going to get negative 3/2 cosine of u. And then remember how u was x squared at the very beginning? So I'm going to plug x squared back into here, and I'm going to get negative 3/2 cosine of x squared. And then now I can evaluate it from 0 to square root of pi. I'm still using the old bounds because these are the bounds for x. These were the bounds for u over here. So evaluating this is going to give me negative 3/2 times the cosine of square root of pi squared minus the cosine of 0 squared, I guess. And then negative 3/2. The cosine of the square root of the square root of pi squared is going to be pi, and then cosine of pi is -1, and then cosine of 0 is 1. So we still have negative 3/2 times -2. Negatives cancel, 2's cancel, and we still get the same answer of 3. And that was part C. Now let's move on to part D. Okay, let's look at part D now. So the integral of 4 minus the square root of x. This is the example of that weird one that I talked about earlier, where it's like not a normal u-substitution, it's like a kind of a interesting one. So remember, the part under the square root is that's what we're going to call u. So u is going to be square root, or it's going to be 4 minus the square root of x. And then now I want to replace everything in here with u. So I'm going to solve this equation for x. So let's isolate the square root of x first. Square root of x is going to be 4 minus u. And then I'm going to square both sides. And I get x is equal to u squared minus 8u plus 16. And then now I'm going to replace the dx with the du. So to solve for dx, I'm going to take the derivative of both sides. And I'm going to get dx equals 2u minus 8 du. Or dx du, and then I brought that to the other side. And then now I can say, alright, I'm going to replace the dx with 2u minus 8 du. So this is the integral of, and then remember, the 4 minus square root of x is u, so I have square root of u. And then instead of dx, I'm going to write 2u minus 8 du. So I'm replacing the dx, and instead of it, I'm going to write 2u minus 8 du. And then this is something that I can solve. So the way I'm going to do that is I'm going to write this as u to the 1/2. I find that that's usually really helpful, like writing square root in terms of fractional exponents. It makes it easier to combine. So combining like that, going to give me 2u to the 3/2 minus 8u to the 1/2 du. And the fractional exponents also makes it easier to integrate. When I add and divide, I'm going to get 2u to the 5/2 times the reciprocal of this, so times 2/5 minus 8u to the 3/2 times the reciprocal of this times 2/3. And simplifying this is going to give me 4 over 5. And then instead of u, I'm going to replace this back with 4 minus the square root of x. So 4 minus the square root of x to the 5/2. Did I give myself enough space here? Minus, and then so 16 over 3. Yeah, I did. Okay. 4 minus square root of x to the 3/2. And then since this is an indefinite integral, do not forget your plus c. And with that, we are done with part D and finished with question 2. Okay, question 3. We're given the graph of f, and we have that g of x is the integral from 0 to x of f of t dt. So g of x is the accumulation function, and we're asked to first find g of 4 and then find g prime of 4. Let's do that. So g of 4, that's going to be the area, this area, from 0 to 4. Right? And the way we're going to find that is by just using the area formulas that we know from like middle school. So it's going to be the area of this this outside square here. It's 4 by 4 square. So we're going to have 4 times, it's a terrible color on the black, 4 times 4 plus the area of this this triangle here, so plus 1/2 times 2 times 1 plus, and then this triangle up here, 1/2 times 2 times 2. So simplifying this gives me 16 plus 1 plus 2, or 19. And then g prime of 4, so this is g of 4, and then g prime of 4, remember how g of x is this accumulation function? So if I want to take g prime of x, that's going to be the derivative of the accumulation function. And remember, the derivative of the accumulation function is just f of x. So g prime of x equals f of x. And then g prime of 4, therefore, equals f of 4. And then looking at our graph here, f of 4 is this point, and that is 6. So you have g prime of 4 equals 6. Okay, now let's look at part B. Part B says, show that g of x is less than 25 for 0 is less than x is less than 5, or less than or equal to. So the accumulation function is gathering area, right? So looking at just the positive part of this function, as x increases, f of x keeps increasing. Sorry, the accumulation function keeps increasing, right? G of x keeps getting larger and larger because you're gathering more and more area as you go on. So the maximum of this function, the maximum of g of x, is going to be at this point right here. At this point here, at x equals 5, because that's where all of the most area has been gathered, right? So if I want to show that g of x is less than 25, I know that g of x is always going to be less than or equal to g of 5, right? For 0 is less than or equal to x is less than or equal to 5. This is always going to be true because in this interval 0 to 5, g of x is always going to be less than or equal to the maximum of g of 5. Okay, so let's find g of 5. G of 5 is going to be, well, g of 5 is going to be g of 4 plus this rectangle, or this triangle here, plus this triangle. So let me find the area of that triangle. It's going to be 1/2 times 1 times 6, which is 3. So g of 5 equal, what's g of 4? Well, we found g of 4 up here is 19, plus, and then the triangle is 3, equals 22, right? So g of 5 is 22, and then we said g of x is less than or equal to g of 5, which is, and then 22 is always less than 25, right? That's just a fact. So we can say g of x is less than or equal to g of 5 is less than 25. Therefore, this is some geometry property, I don't remember what this is called, but g of x must be less than 25. Right, and we've proven that. Therefore, and remember, this is always for 0 is less than x is less than 5. I don't know what's going on after x equals 5. But from 0 to 5, we've proven that g of x is always going to be less than 25, which is what the question asked. We're on to question 4. Okay, so in this last question, we're given the function 3x squared minus 2x, and we're asked to find these two things. So let's start with part A, find all values of c that satisfy the mean value theorem. So the mean value theorem says that for a function f of x, the average value of that function in the interval is going to be equal to f of c at some point, where c is some number in between 0 and 4. So let's find the average value of f of x. So the average value of f of x is going to be 1 over b minus a times the integral from a to b of f of x dx. This is the average value function, or the average value formula rather. So I know since I'm going from 0 to 4, my a is 0 and my b is 4. So this is going to be 1 over 4 times the integral from 0 to 4. And then since my f of x is 3x squared minus 2x, I'm going to write, and this is equal to, like I said, f of c, where f of c is the average value, and c is some number in between 0 and 4. If I plug in c for x here in f of x, I'm going to get 3c squared minus 2c. So what I'm saying here is this is the average value, this is the average value. Find the value of c such that f of c equals the average value. So basically what I have here is an equation, and I'm asking to solve this equation for c. So let's do that. I want to integrate this. Thankfully it looks pretty easy to integrate. It's just going to be x cubed minus x squared from 0 to 4, and this is equal to 3c squared minus 2c. And then putting in a 4 here, I'm going to get 4 cubed minus 4 squared over 4. And then it's going to be 4 squared minus 4, which is 16 minus 4 is 12. So let's bring that up here. 3c squared, 3c squared minus 2c minus 12 equals 0. I don't see a way to solve this without either completing the square or using the quadratic formula, but we have a coefficient there. Completing the square is going to be an absolute pain, so let's just use the quadratic formula. So we have 2 plus or minus square root of 4 minus 4 times 3 times negative 12 all over 2a, so all over 6. It's going to be 2 plus or minus square root of 148 all over 6. And then to decide whether I want the plus or the minus, let's look up here, and we saw, okay, we want c to be in between 0 and 4. So since this is the solution for c, we want to pick the sign that's going to give us a value in between 0 and 4. If I pick a minus sign, since the square root of 148 is obviously bigger than 2, if I pick a minus sign, I'm going to get a negative number, which is not in between 0 and 4. That means I should go with the positive number, square root of 148 over 6. And then I can simplify this and get 2 plus 2 square root 37, or 1 plus square root of 37 over 3. And this is my final answer. If I wanted to check that it was in between 0 and 4, I can say, okay, this is approximately 6. So 1 plus 6 is 7. 7 over 3. Yeah, that's pretty clearly in between 0 and 4. So this seems to be a pretty good answer. Okay, now I'll erase and we'll look at part 2. Okay, part 2. So when I wrote this question, I was motivated by another question I saw earlier that day. So I wrote it in like a different way that you might have seen on example problems, and I just did that to like try to get you outside of the normal problem solving strategies. So here we're finding a value of b such that this satisfies the mean value theorem. So again, let me rewrite the mean value theorem. What it says, we have the average value of function 1 over b minus a times the integral from a to b of f of x dx. This is equal to f of c, where c is in between a and b. Okay, so we want to find a value such that 2/3 satisfies the mean value theorem. So they're giving us the c value. They're saying, okay, we'll give you c. C is 2/3. But what we're not giving you is we're not giving you b. So now let's see what we can do here. So we still know that a is 0. We don't know b. That means, so if I simplify this equation, I'll have 1 over b times the integral from 0 to b of 3x squared minus 2x dx. And then this is going to be equal to f of 2/3, because that gave us the value that satisfies the mean value theorem. And then I can integrate this the same way I normally do. 1 over b times x cubed minus x squared, evaluated from 0 to b, being equal to f of 2/3. Putting in b, I'm going to get b cubed minus b squared over b. And b squared minus b equals f of 2/3. Let's find f of 2/3 real quick. That's just going to be plugging in 2/3 into the function. It's 3 times 2/3 squared minus 2 times 2/3, which is 3 times 4/9 minus 4/3, sorry. And then 3, it's going to give me 3. So I have 4/3 minus 4/3, which is equal to 0. Okay, that's interesting. So what that means is I want to find a value where b squared minus b equals 0, because 0 is f of 2/3. So let's factor this out, and I get b times b minus 1, and then b equals 0, and b equals 1. So do I have two solutions? Well, no, because it says find all positive values of b. And that means we can eliminate b equals 0, and we're left with b equals 1. So what is this? What is b equals, like, what does that mean that b equals 1 is the answer? It means that on the interval 0 to 1, 2/3 satisfies the mean value theorem. Okay, so that was the last question in the integral review unit, and I hope you enjoyed it and found this video helpful and it clarified stuff, and I will see you next time.